or the end-to-end latency. We can use analytical models to develop a control strategy for the aggregation delay. In this slide you see 3 pictures from an analytical model. On the top right picture, the normalized system throughput versus the aggregate traffic injection rate is shown. The aggregate traffic injection rate is the total load in the network. In the middle picture, the MAC layer service time versus the aggregate traffic injection rate is depicted. The MAC layer service time is the time that a packet needs to wait when it is head of line at the service at the MAC layer until it is successfully transmitted. In the lower picture, you can see the MAC layer service delay versus the channel busy fraction. The channel busy fraction is the fraction of time the channel is sensed busy due to successful transmissions or due to collisions. From the analytical model, we can draw a few important conclusions. The first one is that the highest throughput is before the network saturation, shown here. So that we get the peak throughput here, and if we increase the network load further, the throughput starts to decrease. This is because if we have too much load in a network, we have a high collision probability and thereby reduce the actual system throughput. The second observation we can make is that the MAC layer service delay is low if the network load is low or medium, here. In the third observation, we see that the MAC layer service delay increases sharply and right before the network is saturated, which can be seen here. And the fourth observation we can do is that the channel busy fraction is an indicator of how high the network load is. We use this information to develop a control strategy. The strategy is fairly simple and uses the following iteration. If we use a small aggregation delay, we have small packets. That will lead to a higher network load. Can be seen here. If we use small packets, the throughput will be low and the network throughput will be low, whereas using larger packets we get a better throughput. The other intuition is if we have large aggregation delay, we get large packets and a lower network load. And what we would like to do is to tune the network load so that the channel busy fraction is around 70%. In this region, we get a high throughput, but also a low MAC layer service delay. Unfortunately, it's hard to formulate a model that gives us the optimum aggregation delay, because we only get vague and fuzzy information, which is practically not usable in a distributed scenario as we have in the mesh networks. So our idea is to control the aggregation delay using fuzzy logic control. Our fuzzy controller has the following input variables: the channel busy fraction, this is the indicator for the medium load; the delta busy fraction, this indicates the temporal change of the channel busy fraction; and ratio difference, which is a fairness parameter that makes sure that stations that transmit more data proportionally have to delay the packets longer and aggregate more. The output of our fuzzy controller is delta delay max. This is the change in aggregation delay. In the pictures here, you can see how the membership functions for the input and output variables are defined. Similarly, in the table below, you see the fuzzy rules in a tabular form. The fuzzy controller works as follows. we have the membership functions that were defined in the previous slide, and we have the fuzzy rule base that was also given in the table on the previous slide. The crisp input variables, for example the channel busy fraction, which is measured by the network card, by the wireless network card, goes into the fuzzifier, which translates the crisp value, for example a channel busy fraction of 60%, into a fuzzy value. The fuzzy value would be, for example, channel busy fraction is medium with a probability of 30% and is high with a probability of 10%. Then we use the fuzzy inference engine to calculate our output. That output is defuzzified, and so we get an output value, for example, for the change of aggregation delay. I would like to demo here first what is the impact of the channel busy fraction, why this is a good input parameter into a fuzzy controller, and how the channel busy fraction is connected with the network load. In this example, the nodes here will generate 12 voice calls each, and this one will also generate voice calls, or you can also think of a client that is connected in the internet and generates the voice calls. And then I will measure the channel busy fraction on this link here, and also the round trip time, to give an indication of how high the... In this demo, the relationship between the channel busy fraction, the aggregation delay, and the round trip time is shown. On the top left window, you see the round trip time as measured by ping. On the right window, you see the channel busy fraction measured on the internet gateway node. In the lower window, you see what is going on in the demo. We first set the aggregation delay to 0.1 milliseconds, a very low aggregation delay. Then we start traffic using mgen. You can see that the round trip time immediately goes up to 150 milliseconds and more. Also, you can see that the channel busy fraction is now at above 70%. In the round trip time window, you can see fairly big variation of the round trip time. This is an indicator that the network is unstable. So for the current traffic, apparently the aggregation delay we are using is not enough. So the network gets overloaded because too many small packets are sent, and the result is a high round trip time, high packet loss, and so on. We can see that by looking at the channel busy fraction. We now stop the traffic and change the network configuration. Instead of using an aggregation delay of 0.1 milliseconds, we now use an aggregation delay of 10 milliseconds. This allows us to have more aggregation opportunities. We start again the traffic, and as you can see, the channel busy fraction goes up. But this time, the round trip time stays low. Now the channel busy fraction is around 50%, which is much lower than before, although we sent the same amount of traffic as before. Using the higher aggregation delay gives us more aggregation opportunities, which leads to lower overhead and to fewer collisions. This also has positive effects on the round trip time, as you can see from the plot in the round trip time window. So from this demo you actually see that not always a small aggregation delay is good. Sometimes you have to use a large aggregation delay, but by that you can still reduce the round trip time compared to using a small aggregation delay. And the key here is to find the aggregation delay that is good for the current network load. the network load is.